Welcome back to Code Deconstructed. In this episode, we'll take a look at xmonad, a window manager for X11. I remember when xmonad was released that it was the first Haskell application I remember gaining popularity outside of the Haskell developer community. It's also interesting for a Haskell program because the job it's doing is inherently stateful, managing the windows and workspaces in an X session. And finally, the code for xmonad is very small and concise. It's something you could conceivably read all the way through, and I recommend it if you're inclined to. In order to follow along with me, you'll need the source code for xmonad version 0.11. And you'll also need X, so if you're not already on a Linux or BSD type system, you can use an emulator such as the freely available VirtualBox. Leave me a comment if you'd like me to build a virtual machine image with all of the software that I'm using here. And if there's enough demand, I'll make one available. Let's start by looking at what xmonad does. I'm using xmonad currently, but in order to make things a little bit clearer, I'm going to start an embedded X session with Zephyr. Zephyr creates a new X session inside of an X window. Here, you can see it outlined in red. And I'll start an application inside of the new X session, xeyes. And you can see that when I'm inside the window, xeyes can see the mouse. But when I'm outside, it can't. It's like there's no input going to that X session. Let's start another application, xcalc. And you can see that xcalc has drawn itself on top of xeyes. And this is where a window manager like xmonad comes in. It manages where on the screen these applications draw themselves to. So let's start xmonad now. And you can see the default behavior for xmonad, and that is to tile the windows, and in this case, side by side. So when we move the mouse between them, focus goes between them. We can also use the keyboard to change some of the layout. But before doing that, I need to load my keyboard settings for my current session into the new session because I use Colnag layout, and if you use a non-standard layout, you will probably have to do the same. So now inside of this X session, if I press Alt space, which is the default mod key for xmonad, which controls its behavior, you can see that Alt space cycles through some different layout. And Alt J moves the focus between different windows. The same with Alt K in the other direction. Alt space again brings us back to the default layout. And let's add a third window just to make things interesting. We'll add an X term. So again, here are the different layout options we have. We can also use Alt Shift J to change the stacking order of the windows, or the position that they display in each of these layouts. So that's the basics of xmonad. It might not be your preferred way of managing windows. There are other layout options, and there are other window managers, but it tends to be popular with people who like to use the keyboard more than the mouse. I should note that the only reason that xmonad inside of xmonad is working is that I have the mod key mapped to a different key in each session. I'm not using the default config in the outside X session. I'm using this one here. Let's explore how xmonad is managing these windows. We'll start by opening the source to stackset.hs. And at the beginning of this file is a comment that explains what a stack set is. This diagram, I think, does a good job of summing it up. It manages a list of workspaces and windows. So it's a data structure that's a list of workspaces, and each workspace is a stack of windows showing the order that they're stacked in and the one that currently has focus. I haven't shown you workspaces yet, so let's take a look at that right now. A workspace allows you to keep track of windows separately. This is called spaces in OS X or virtual desktops in Windows, I think. And in xmonad, by default you get 9 virtual workspaces, and you can switch between them with Alt 2, Alt 3, Alt 1, which is the default, and so on. So let's switch back to my second workspace, which is Emacs, and continue looking at the code. Now, the stacks themselves are stored in a data structure called a zipper, and this is an interesting, purely functional data structure that's a more efficient way of representing the stack. You can read about them elsewhere. I'm not going to go into the theory here. Instead, we'll skip down to look at the actual code. So here's the stack set. It's basically a record showing the currently focused workspace, any non-focused but still visible workspaces, which is possible when you have more than one monitor, a list of hidden workspaces, and then any floating windows, which we won't be getting into. Further down the file is a stack, and this is what we'll be focusing on. It's the zipper we mentioned that holds the focused window, the windows above this window, and the windows below this window. If you haven't seen the exclamation mark in a type signature before, don't worry about it now. We'll get to that later. Now, I think it would be useful to understand the program by watching the stack and the stack set change as xmonad is running. The first step to doing that is loading xmonad into GHCI, and we'll do that by first killing the xmonad we started earlier. And you can see that the windows are still there and they'll still respond to input and everything else, but xmonad itself is gone, and you can test that by pressing Alt space. And the layout doesn't change, the space just goes through to the X term. So within the xmonad source code, we'll run cabal dev GHCI, but we want anything launched from inside of GHCI to have the display environment variable set to 1. And now xmonad hasn't started yet. The program's just loaded into GHCI. And in order to start that, normally you would type main. But in the case of xmonad, that's not exactly what we want. And to understand why, you have to understand how xmonad is configured. In the early days of xmonad, the way you configured it was by editing the source code and recompiling it. Things are a little bit more friendly now, but the process is essentially the same. You create a .xmonad directory, and inside of that you have xmonad.hs. This is a minimal configuration. You saw my more complex configuration earlier, but you're essentially defining your own main function. And when xmonad starts, the main that it was compiled with, let's actually take a look at that now. It's in main.hs at the top level of the source directory. What it does is runs build launch before running xmonad. And build launch looks in the xmonad directory for a custom xmonad that you build through xmonad recompile. So if we were to run the main function from GHCI, the main function would call out to the shell to execute the custom xmonad, and we'd be outside of the code we're modifying. So instead, we'll use xmonad default config. And these are defined in the xmonad module. And so now xmonad is back. So now we have xmonad running inside of GHCI. The next step is to modify the code to print out the state of the application as it's running and as it's changing. To do that, let's take a look at the file core.hs in the source code. And here the state of the application is defined, xstate. It's a record with a number of members, but the one we're interested in is the window set, which is defined as a stack set that we saw earlier. One other thing to look at is here, the xmonad. And this is what xmonad gets its name from. It's a monad built up of other monads. There's a reader monad that carries around the immutable configuration data for the program. There's a state monad that manages the X state we're interested in seeing. And there's also an I/O monad allowing xmonad to perform I/O operations, the most important of which are the X11 I/O operations that actually make things change on screen. Whatever your level of understanding of monads is, the important thing to see here is that any function in the xmonad has access to the application's state using any function defined by the state monad class. To see some examples of that, let's look in operations.hs. And you can see some functions here that are defined in the xmonad. And much of the code here uses the modify function, which takes the current state and sets a new state to change the overall xmonad application state. Now, what this means for us is that we should be able to make a modification to how this state monad transformer here works and print out all of the state changes as the application is running. To do that, we first have to remove the automatically derived monad state instance, and then add our own. The one that the compiler comes up with on its own would look something like this. Instance monad state x state x, and you need to define two functions for a monad state instance. Get, which gets the state, and put, which sets the new state. Don't worry if this doesn't make perfect sense. What's important is that we have an instance definition that we can now modify. So we want to see the state every time it changes, and we can do that by tracing the state every time it's updated with put. So let's trace show the new state each time a put happens. Trace show allows us to cheat our way around the type system. It actually does some I/O by printing something to the screen, but the return type is whatever the second argument is, in this case put s. So we can use it anywhere in a Haskell application, with the warning that it's really meant just for debugging like we're doing now. And trace show is part of the debug.trace module, so we'll add it to the imports. And finally, we need to be able to show X state, and it doesn't have a show instance currently. We could try deriving it, but some of the members don't have show instances or derivable show instances either. So we'll need to create our own show instance, which is fine because we really don't want to see everything in the application state. We just want to take a look at the window set. So let's make xstate an instance of show. And show will just be show of window set. We'll save it, and no, we don't want to update the copyright. And now let's test our modifications. So we'll quit the currently running instance of xmonad with Alt-Shift-Q. And I'm going to go ahead and exit GHCI as well, because in my testing, something is left around that interferes with the next run of xmonad. So we'll enter GHCI again. And this time we're in the context of an interpreted main, so we should be able to run xmonad default config. And it worked. We have a lot of state on screen. You can see it being updated as we move the focus around. And in fact, it's a little bit too much state to work with comfortably here. You can see that xmonad by default has 9 different workspaces. And I think it would be a little bit easier if we only had 2 for testing. So we'll quit xmonad again and leave GHCI. Re-enter GHCI. And this time, instead of the default config, we can make a change to the number of workspaces. And to see how that's done, let's take a look at config.hs, default config. And the default config has workspaces equals workspaces. So let's look up workspaces. And workspaces here, you can see the code for. We can just modify this to reduce the number of workspaces we have. So default config workspaces equals map show 1 to 2. And let's try that. All right, so now you can see the state that's changing is able to fit in the terminal beneath the X window. As I move around the focus, I'm watching the stack, which is that zipper we read about in the source, and seeing it update. I also notice that current is set to workspace 1, and hidden is a list that contains workspace 2. Let's try switching to workspace 2 with Alt 2, and then back to workspace 1. Let's also see if we can notice any change when we change the layout with Alt space. And if we change the stack position for a window with Alt-Shift-J. Now let's try adding a couple more windows to see what else changes. And we should be able to launch those directly from inside of this session. So let's launch a new xterm and one more. And I'll move the focus around so you can track what's happening in the zipper. And again, shifting which window is in the main slot. Now that we've seen the zipper or stack in action, we should have an easier time understanding the source code for it. So let's switch back to take a look at it again. A stack is the item that's currently in focus, which in this case is a window identifier, along with the items above it and the items below it. Up and down are sometimes referred to as left and right, somewhat confusingly, And the reason for this is that a stack is usually visualized vertically and a list visualized horizontally. And since a stack can also be thought of as a list broken into 3 parts, that's why you sometimes see left and right. Let's look at a function that manipulates the stack. A simple one should be moving the focus. So here's focus up prime, which takes a stack. Again, it's the item in focus, the items above or to the left, and the items to the right. So L's and R's here probably stands for lefts and rights. It then takes the head of the items above and makes that the new focus, and takes the old focus and moves it to the head of the items below. Let's switch back to our modified version of xmonad and just see if we can see that in action. So the focus here is on this window. We'll put the focus on this window here. There are 2 items above it and 2 below it. So when we move the focus up, the head item from up is moved into focus and the focus is moved into the down list. The reverse happens when we switch the focus back down, and you can see the up list growing as we go down and the down list growing as we go up until the up list is empty. And that's all we have time for on this episode. Again, leave a comment if you'd like me to build a virtual machine image that includes everything here so that you can play with xmonad yourself. Thanks for watching, and I'll see you next time.